the invited talk of today. I'm glad to greet Lidia Tendera, who is working on a broad chart of decidable fragments of order logic. I think she started her PhD in the 90s on bounded variable fragments, and she has worked on different kind of guarded fragments. And today she will talk about the FLUTED fragment, which has almost archaeological origins. So Lidia, welcome. The floor is yours.
Thank you very much for the introduction, and thank the organizers to inviting me here to speak to this audience about my recent research joint with Ian Pratt-Hartman and Wiechek Schwast, which at some moments of time looked maybe more like obsession than serious things, but archaeology is also maybe a little bit about it. So my talk I divided into 3 parts. In the first part, I will present you the FLUTED fragment in details and give the main properties, a little bit of history. Then I will speak about some extensions and restrictions, and time permitting, maybe in the technical part, I will manage to sketch 1 or 2 results which I will review in the first 2 parts. Let me start recalling the crucial decision problems for this talk and for this area of research, namely the satisfiability problem, here denoted by set of L, where L is analogic. And in this problem, we are interested in the following question: given the formula phi, is it satisfiable? Namely, does the formula admit a model? In the finite satisfiability problem, we additionally want to know whether our formula admits a finite model. And since the 30s of the previous century and the highly celebrated results by Church, Turing, and Trachtenbrot, we know that if our logic is the full first-order logic, which I denote here by FO, then both of the decision problems are undecidable, in fact, also recursively inseparable. And this, on one hand, looks like bad news, but naturally leads to a choice of various possibilities. For example, we can say, okay, we consciously accept the undecidability, but we try to devise algorithms which will be inherently incomplete, hoping that in several practical cases they would still perform relatively well. The other response can be consider some fragment of the logic. If this logic is undecidable, maybe we can restrict the logic and this way gain a decidability. Or together with the second response, we can also restrict the class of structures where we look for models of our formula. And in this talk, I would address the last 2 responses. I will not mention anything about incomplete algorithms. It's also important to recall that in some cases, the 2 decision problems, the satisfiability and the finite satisfiability problems, coincide. This is the case when our logic has the so-called finite model property, which means that every satisfiable formula has a finite model. And we also know that if the logic we have in our hands is a fragment of first-order logic, then finite model property itself implies decidability. In some cases, finite model property also comes with a bound on the size of the models, which also allows us to give to devise some algorithms within some time bounds, but even without it, we immediately get decidability from the finite model property itself. And these are the problems, the decision problems that would be important for this talk. It's known that many other reasoning problems are studied, and some of them also can be reduced to the satisfiability or finite satisfiability. So that's why these problems are also sort of the base, called sometimes classical, the ones which are usually the first to study. And now when we think about restricting a logic to some fragment, we can somehow think along two lines. One would be, let's look at some fragments which are suitably motivated. We have, for example, some ontology written formally, and we have there some rules, formulas. We can look what kind of conditions are really used there, what kind of restrictions we could impose, and what does it mean for decidability. And from the other hand, we can sometimes also restrict a fragment or restrict some conditions just in order to understand what the reason for high computational complexity is, or for undecidability. So it's not always that we need we get very strong motivation from practical side. Sometimes we are more interested in understanding the actual reasons for good or bad properties. And one source of motivation that in the past 25 years roughly inspired the development or somehow identification of several interesting fragments of first-order logic comes from modal logic, which was already known, that has very good model theoretical and algorithmic properties, was used in various practical areas, and could be translated to first-order logic. I'm not going to present this translation in detail, but I would like just to use this one example. And so naturally, there is an image of the translation, of the standard translation of modal logic, which must be some fragment of first-order logic, which is undecidable when we take it the complete fragment, the complete logic. But what is the restriction? What the restrictions are? And one of the first observation was that in this translation, we don't need to use more than two variables. So here in this example, when this box subformula was translated by this universal quantifier with the variable z, it suffices to observe that in this subformula, the variable x doesn't occur. So we could as well replace the z by x. And this is a pattern that repeats. So this is why we can explain good properties of modal logic in some sense by referring to the two variable fragment of first-order logic, which I denote by writing the number of variables as the superscript. And this fragment is known to have the exponential model property. So each satisfiable formula of the two-variable fragment has a model of at most exponential size, and therefore this logic is the decidability problem, the satisfiability and the finite satisfiability problems can be decided in next time. We can simply guess a model of the size and verify that it's that the structure that we guess indeed is a model for our formula. So this was about the two-variable fragment. But when we look back at the example, at the translation, we can also observe other syntactic properties that the formulas that we get from this translation have. And this inspired the introduction of other fragments, in particular of the guarded fragment, where we restrict only the way quantifiers are used. They are supposed to be relativized by atomic formulas, exactly like it happens here in these examples. Another fragment is the unary negation fragment, where the only restriction is applied to the usage of negation, where negation is only allowed to be used to be applied to formulas with a single free variable, and this is again the case that we see in this example. Moreover, this standard translation also, the image of the standard translation is also contained in our hero for the stock in the FLUTED fragment, where we require that the variables that we where we fix in advance an order in which variables are allowed to appear in atoms and in subformulas. I will explain this in detail on the next slide. So on the slide we have two examples of FLUTED sentences written. Actually, we have two examples of sentences in natural English written in the FLUTED syntax. The first one, no boy admires every girl, can be written using two unary predicates, boy and girl, and one binary predicate, admires. And the important property here is that this atom contains the variables x1 and x2 exactly in this order. We cannot have x2 and x1 if this is the fixed order. First x1, then x2. And there are no other restrictions. Apart from that, Boolean connections, Boolean connectives are allowed join formulas that agree on the last three variables. And this is the case that we have. This formula ends with x2 and this atom ends with x2, so we can join them by this implication. Quantifiers also are restricted to bind precisely the last three variable of the subformula to which they are applied. This is probably even better visible in the second example, where we have a unary predicate lecturer, student, book, a binary predicate need, and a ternary predicate land. And now this this atom, for example, land x1, x2, x3, it must, if land is a ternary predicate, then it needs three arguments here, but the only possibility here is that x1 appears before x2 and x2 before x3. So actually we don't need to write here these variables if we know which one is the last one. And similarly here, so taking this into account, we could just omit the variable x3 when we know that this quantifier binds the last free variable of the subformula to which it is applied. But then the same property applies also to this conjunction and this quantifier, so we could omit actually the variable x2, and exactly the same property applies to how this x1 is allowed to, where it is allowed to appear and to occur, and to this quantifier. So in fact, in FLUTED fragment, we don't need to write the variables at all. We could just write the quantifier, and if we know the arity of the predicates, then we can go back and add the right variables where they have been meant. Formally, first one more remark concerning the name for the logic. The allusion FLUTED seems to be architectural, namely when we organize the quantifiers and the atoms in separate rows, then we can align them in such a way that the same variables form vertical columns, like we can see here on this picture. I hope these are the previous two examples. So x1 is here and here and here, and then x2 is aligned on this green column, x3 in this red column, and this is the allusion to the floatings that we have in some ancient fluted columns, or the floatings that we have in fluted glass. On the slide, we see the formal definition of the fluted fragment, but I think I don't need to go now in detail after this explanation. The important thing is that we first fix the order in which the variables will occur, and whenever we write an atom, then the atom will have some continuous subsequence of the variables of this fixed order. So there would be some last variable, and then the sequence of variables will be continuous here, depending on the arity of the predicate letter. And I will denote the fluted fragment by FL. And in this fluted fragment, we will also identify the fragment denoted by adding a superscript M, which is then the intersection of the fluted fragment with the M variable first order fragment. Just to balance the examples and the definition, a few formulas that are not fluted. So for example, none of the formulas expressing reflexivity, symmetry, or transitivity of binary relations are fluted. Here we have a repetition of variables in one atom. This is not allowed. Here we have an atom which contains variables x1 and x2, but in the wrong order. This is the fixed order, so this is allowed, this is not. And in the third formula, we have an atom which contains x1 and x3. This is not a consecutive sequence, so this is also not fluted. And I would also like to mention that there is a contrasting fragment studied by Andreas Herzig, called the ordered fragment, where the variables are lined up the other way around. So here it is in the ordered fragment, it is required that Boolean connectives join formulas that agree on the first variable. So this example is ordered. They agree on x1, but it's not fluted, and this formula is fluted. These two atoms agree on x2, but it's not ordered. And the audit fragment turned out to be also decidable, and it is in P space. And it calls formulas of the audit fragment can be also translated into the FLUTED fragment. And now a piece of history. We've already seen on one of the slides that it goes. The history seems to go back to '68 when Quine noticed that the Skollem's proof for the monadic fragment of first order logic can be generalized to homogeneous M-adic formula. So in this fragment, we have in the signature formulas of the same arity M. And then it was later claimed that this proof should be further, that this proof probably generalizes to what I now introduced as the FLUTED fragment. This observation has been questioned later by Noach, and then there was a sequence of papers starting with the paper by Pardy in '96, where the finite model property for the FLUTED fragment was shown. And then in the last paper of the sequence, it was claimed that the fragment has the exponential size model property, which would then mean that its satisfiability problem is in next time. And this last paper was actually the reason why we became interested in this fragment. We thought, okay, there was a nice fragment. Next time complete. This is not too much when we look at other fragments that are studied, developed. And we thought it would be interesting to see what could be added to this FLUTED fragment in order to still stay on the decidable side. And it turned out that it's not so easy because this claim is false. So what we've shown is the following. Any satisfiable formula of the FLUTED fragment with m variables has a model, a finite model, but of m-tuply exponential size, where this, namely of a size bounded by the tower function, where we have a tower of tools of height m, and the last parameter is a polynomial in the length of the formula. So we confirmed that the fragment has finite model property, but we get an upper bound of m-tuply exponential non-deterministic in time for the fragment with m variables. And on the other hand, it turned out that satisfiable formulas with 2m variables false models of m-tuply exponential size, which could be also generalized to show that the satisfiability problem for the fragment with 2m variables is in fact hard for non-deterministic m-tuply exponential time. Which implies that the whole FLUTED fragment is in fact non-elementary. So later, I mean, there was this bound. So we have 2m variables for the lower bound. So the complexity, in fact, of a fragment with m variables is between m½ next time and m next time. We worked a little bit on trying to improve the upper bound. We managed to reduce the upper bound by 2 levels. And this gives us a tight complexity bound for the fragments with 3 and 4 variables, FLUTED fragments with 3 and 4 variables. And then the bounds are not tight anymore when we start with 5 variables. So this is this was about the fluted fragment itself, and now I would like to talk about some possible extensions. And so far we had the finite model property for all the fragments that I mentioned, and this is not this is something that we can easily lose when we add a little bit more expressive power. So imagine now that we try to write a formula which would a satisfiable formula which would induce some infinite chain of elements in the model. Here's one example. When we allow ourselves to add so-called counting quantifiers, these are quantifiers where we say there exists at least or at most m elements satisfying some formula. And in fact, this quantifier, there exists at most one suffices to induce such an infinite chain of elements in any model for this conjunction. So the green conjunct requires that in the model we would have an element that is here denoted by the green dot, where no incoming R edge is allowed. R is a binary relation described in this picture just by arrows. So this green element needs some, requires some witness to satisfy the first conjunct. And this must be a new element because we cannot create a loop. And this new element also requires a witness. And again, we cannot loop back to this green element, and we cannot create a loop here because it would then falsify this the last counting quantifier. And therefore, the conjunction of these three formulas induces an infinite chain of elements. And we could achieve the same without counting quantifiers using only two variables and an additional requirement that our binary relation is transitive. So now when we look again at the same picture and we remember that the arrows depict a transitive relation, then again, if we try to look back from some element, then this would create a cycle in the model, which we forbid by writing such a simple formula that the relation is irreflexive. And now this requirement that R is irreflexive is not fluted, but could be written as fluted if we additionally allow equality in the fragment. Yeah? So this formula now for all x for y, if x y, then x is different than y, would be a proper formula of the fluted fragment with two variables and equality. So we have here either counting quantifiers or somehow a stipulation that some relations are interpreted as transitive relations. This requirement, of course, cannot be defined in using two variables. This needs to be somehow imposed separately, and this is what has been done already in many other cases. So we, when we want to add transitivity to some fragment where we only have two variables, we usually say that we will consider some classes of structures where the interpretation of one or two or more binary relations is required to be transitive, or some special order, partial order, which also requires transitivity. So this has been this approach has been used, and it's known that when we add this kind of, when we consider the two-variable first-order logic, or even the guarded two-variable fragment with some transitivity axioms or under classes of structures where some relations are transitive, then we relatively simply get undecidability. And now what happens when we add the same requirement to the possibility to the fluted fragment is shown on the slide. So the first row talks about the logics with no transitive relations. And then when we have one transitive relation in the signature, no equality, then the fluted fragment, the whole fluted fragment, no matter how many variables we use, has still the finite model property and is decidable in m next time. So here this m is exactly the number of variables that we allow here. When additionally we add equality, we've seen on the previous slide that we lose finite model property very easily, but still in the fluted case, both the satisfiability and the finite satisfiability problems are decidable, and we have here this bounds, m next time for the satisfiability problem, m plus 1 next time for the finite satisfiability problem. The bounds are not tied, but at least we know that decidability holds. And then when we add more transitive relation, when we have two transitive relations and we look at the full FO2, so the two variable first order fragment, this is already undecidable. Two transitive relations suffice. In the fluted case, we don't know. So this is an open case. But if we have additionally equality and two transitive relations, then already the two variable fluted fragment becomes undecidable, and without equality but with three transitive relations, this is also undecidable. So this is somehow the overview of the situation. What happens if we add transitivity to the fluted fragment? And now a few words about the possibility of adding counting quantifiers to the fluted fragment. Counting quantifiers, here was some example that should motivate this kind of logic. At most 3 lecturers introduce a professor to at least 5 students. So this is proper formula in the fluted fragment with counting quantifiers, can be written as follows in the variable free syntax. The second example illustrates the usage of equality. So every absent-minded professor introduces some student to himself, and this phrase to himself can be expressed if we have equality in the language. And we know from the previous research on various fragments that if we add counting quantifiers to FO2, then we get a logic that is decidable and next time complete. And now the newest results obtained by Ian show that we can add counting quantifiers to the whole fluted fragment, and we still don't lose the finite model property. We don't have equality here, it is only counting quantifiers, but we still are in a decidable fragment. Moreover, we can also study the so-called semi-fluted fragment with counting quantifiers, where the semi-flutedness means that fluted restrictions apply only to subformulas featuring at least 3 variables. So in the semi-fluted fragment, we have the whole power of C2, and this flutedness is also only important for formulas with at least 3 variables. This is similar in flavor a little bit to the tree-guarded fragment that has been also recently identified, an extension of the guarded fragment. And so still, in the semi-fluted fragment, of course, we don't have the finite mode property, because even in C2, this is lost, but this is still on this decidable side of the world. Open questions left from this that I already mentioned. We don't have tight complexity bounds starting from the fragment with 5 variables. It's probably a separate question if it's important to know or in how many cases we actually need more variables. I recall that I've heard some claims that 5 is probably the limit of reasonable number of variables that we use in normal speech. So maybe from some linguistic motivation, this is somehow the border. And I mentioned that the situation with 2 transitive relations without equality for the 2 variable fluted fragment is not clear. But the bigger, the more important question is probably about applications. In view of this recent result, that we can preserve the full power of C2, of the 2 variable logic with counting, and even add more, I think there would be some reasonable applications. I would be also thankful if anybody can share some ideas about it. And now, time permitting, I believe I can still keep your attention for a moment. Maybe I would try to mention a little bit about some technical details behind 1 or 2 of the results I mentioned. The first one on the undecidable side, perhaps. So the 2 variable fluted fragment with 3 transitive relations is undecidable. The proof goes, of course, by a reduction of some well-known undecidable problem. It's by a reduction from the tiling problem. But before I recall this, I would like to mention what is shown on this slide. On the slide, we have arrows which are meant to indicate various transitive relations. So the color black, red, and green. The arrows of these colors indicate elements that are in one of the 3 binary transitive relations. And at the moment, this should be read just that there is some element located in the grid, in the origin, and it is required to have a black witness. That is located somehow because I want to locate it there. There's no reason to draw it this way, but I want to draw it this way. That is located in this node. And then this element has another weakness that is located in this node of the grid. And we have here, and this chain, it actually is some kind of BOUSTROPHEDON order, which is bijection from natural numbers to pairs of natural numbers, where each next element in this chain is at distance 1 from the previous one. Yeah? So this is somehow such a chain, such a sequence. And now it's not clear from this picture why this sequence should continue forever. What I believe you can imagine is that if we add some additional unary labelings, that we can ensure that an element that has some kind of label gets a witness which has some other label, and we can use maybe some 36 labels to identify to distinguish the nearest witnesses somehow from each other. And then we add some additional formulas, universal conjuncts, which say if we have two elements, like here this one, the element located in the node 1, 1, and the element located in the node 1, 0, and they are connected by the black transitive relation, then they should also be connected by the red one. This is in our logic, there is no problem. And then this induces an additional transitive connection. So if this red path denotes a transitive relation, that this means that in particular the element located in the node 1, 1 will be also connected by a red arrow with the element located in the node 1, 2. And then again, we have some conjuncts which says if this kind of elements are connected by the red relation, then they must also be connected by the green relation. This induces a new path of the green relation and some new connections. And this way, the picture, the previous picture, when adding the additional conditions and drawing some connections induced by transitivity starts to look a little bit like this, and this already reminds you perhaps some sort of grid-like structures. What is important in the structure is that elements that we located in the grid, that the neighbors in the grid are always connected by at least one of the transitive relations. And moreover, the transitive paths do not connect elements that are far away. They connect only at most 3 columns and at most 3 rows. Of course, this needs some proof, but these conditions, having these conditions in hand, we can reduce from the tiling problem, where we are given a finite set of tiles and 2 subsets of the product of the set of tiles that define the so-called horizontal and vertical constraints. And we say that a tiling system tiles an n times n grid if there is a function which assigns to each node of the grid a tile from the set D, such that adjacent nodes are assigned tiles that satisfy the horizontal and the vertical constraints. And we know that the problem of checking whether a given tiling system tiles an n times n grid is undecidable. So we take, to complete the reduction, we take the formula that we write in order to describe this intended model that I only showed on the picture, with free transitive relation, and we add some additional formulas which say that nodes in these models must be assigned some unary predicates which describe the tiles of the finite set of tiles of our tiling system, and the formula that every node encodes exactly one tile. This is a unary formula, so this is of course FLUTED, and then the vertical and horizontal constraints should be satisfied, and these are formulas, FLUTED formulas of this form. So we say that if we have a node in our model which satisfies some kind of label, and it is assigned a tile D, then every node which is its vertical neighbor, assigned this kind of label, and additionally is connected to this first element by one of the transitive relations, satisfies some D prime, so is assigned some tile D prime, such that this D with this D prime together are allowed in this vertical constraints. That actually two formulas, because the transitive relations in our intended models, they don't go always upwards. In some cases they go up, in some cases they connect the upper element with its lower neighbor. That's why we have two types of formulas which address this, distinguish these two cases. And similarly, you handle the horizontal constraints. In fact, it's not the construction can be a little bit simplified. I mean, we need this kind of BOUSTROPHEDON order, but it could be a simpler order like this one, and a little bit different generation rules, which also with the same idea that we follow this this BOUSTROPHEDON order, and then we add some conditions that allow us to generate this transitive connections between elements that are close in the grid, but not between elements that are far away in the grid. So that's I think that's it about the undecidability proof, and maybe just a few remarks about the upper bound, the improved upper bound, which I mentioned. So one thing that is similar to many fragments, when we prove decidability, we usually normalize the formula. We prove some kind of normal form lemma that allows us to simplify reasoning. For the FLUTED fragment, the normal form that proves to be useful looks as follows. So here, for all m-1, this should be, this denotes a block of m-1 universal quantifiers. So the normal form FLUTED formula with n variables has some existential conjuncts of this form, a block of m-1 universal quantifiers, and the formula mu I, which is quantifier free, and then it implies some formula exists gamma I, and this gamma I is then also quantifier free. And in this, in the second part, we have here universal quantification. And the normal form lemma just says that we can restrict attention to formulas of this form. And having this normal form lemma, the next step to improve the upper complexity bound was to show two things. First, for every m greater or equal 3, there is an exponential reduction from the fragment with m plus 1 variables to FLM. So we can reduce the satisfiability problem for formulas with m plus 1 variable to m, but at each step we pay one exponential. And then the fragment, the base for this result is the free variable fragment, where it is possible to show that it has already the exponential model property. So this is actually where we gain this -2. Yeah, because in this reduction, each step costs an exponential, but since FL3 is in next time, then these two results give us the improved upper bound that is tight up to m equal 4. But an interesting thing is also that this kind of reduction can also be performed for the fragments where we have one transitive relation or one transitive relation inequality, or FL with counting quantifiers. Not exactly the same, but somehow in a similar way. So this reduction proved to be useful also to get decidability for the other fragments, where we must go down to the corresponding two variable fragments. That's why there is an additional level in complexity. About hardness, I will not say anything more because I think my time is over. I just mentioned that this is once again that this fragment, the whole FLUTED fragment, is non-elementary, and I think I will thank you at this point.
Thank you, thank you, Lidia. We are ready for questions from the audience. If you want to just unmute your microphone. Okay, I see clapping. Question maybe. So I'm very intrigued by this terrible succinctness of this logic. Obviously, if you express something in the third level, you're I mean, it's like saying something in the first level, but very, very much shorter. Do you have a notion of elementary equivalence that would match the FLUTED fragment? I mean, how can I tell that something is not expressible in the FLUTED fragment? How do you do that? No, something like you take by simulation for the model logic, but then this k variable Ehrenfurcht-Fressé games for the k variable fragment. Your microphone is still off. Yes.
This is an interesting question. I've been pondering a little bit about it, but I don't think I have a good answer at the moment. We still don't understand this logic too well, I think. Yeah.
Yeah, I agree. It's very, very mysterious.
I'm sorry.
Can I say something? So I think that, can you hear me?
Yes, yes.
Okay, so together with my colleague from Finland, we have an advice game for FLUTED fragment, ordered fragment, and also forward fragment of first order logic. So it's all about specifying that, you know, the tuple you play a game on fits into this forward fashion. But it's somehow similar, very similar to advice games and also to guarded advice games or guarded by simulations.
Mm-hmm. So you use some kind of locality, like in the normal form that Lidia showed. Some kind of extension.
I mean, it's not published yet, but it's an ongoing work.
Thank you very much for the comment. I had some gossiping about some results, but I planned even to contact Bartosz before this talk to make sure what it is. So I'm very happy that Bartek is present at the moment here.
Okay, thank you, Bartosz. So, are there more questions before we go to the gather room? Patrice, please.
Just some kind of dual question, because you looked at satisfiability, the existence of a model, but is there something known about the difficulty of checking whether some structure satisfies some formula which is in the FLUTED fragment?
Not that I know. I mean, nothing. I don't know anything specific. Anything new? I mean, apart from the results that we know already from other fragments.
Thank you.
This is. I mean, again, thank you for the question, and I think it would be worth checking. Yeah, what's the situation?
Since you have no variables, so this is something that often people in linguistics are attracted. I mean, you know, it doesn't look like mathematics. You can write them without variables. So do you have reports from people in linguistics trying to go for, I mean, to understand the experimental use of this fragment?
I haven't managed to get in close contact with people who could be interested in this result. There was some motivation in some of the first papers, exactly from this field, that this sounds natural. It is much less natural to permute variables when we talk natural language. But so far I haven't reached to this community. Probably we need to look for a good place where we could meet. It's more a little bit more difficult at the moment as well.
Well, they can learn a lot from you. They should come.
Yeah, but it's not so easy to meet nowadays. I mean, if you have an idea whom to maybe invite to this area, I would also be very grateful for suggestions.
Well, it was very good to meet you. So thank you everyone for attending this session, and we'll be on Gather right now and back in, I think, 15 minutes. Is this right, Markus?
No, it's 30 minutes. So it's
30 minutes. So we have a very long break now. Thank you, Lidia.
Thank you very much for your attention and for the invitation once again. It was a big pleasure.
Bye-bye. See you in a moment on Gather. Bye.
Thank you.